Good afternoon.
Good afternoon, sir.
Yeah, good afternoon. Okay, only two of you, so I'll wait for some more people to join. Okay, so you have the timetable with you, this timetable of classes.
Yes, sir.
Okay. So this is your first class today. In morning you had a class today, no?
Sir, in our routine is there, but sir did not take the class. No,
Oh,
sir.
okay. Anyway, so yesterday we learned about work done in an isothermal expansion. So today we'll learn about work done in an adiabatic process or adiabatic expansion. So I don't have the note. So today directly I will discuss from the book from where I would give you the note so that it's easy to understand. Okay, so let us start. I think people will be joining. Okay, so let us start today and I will share something. Give me 1 minute. Okay, I hope you can see this screen. This is the same book actually which I follow. This is the refresher course book of S. Chand, BSc Physics, S. Chand refresher. So here actually it's quite descriptive book. So questions, answers, numerical problems, those are given. Okay. Anyway, so today's topic is work done in adiabatic process. So anyway, so what is an adiabatic process? I think I have explained a few times before. So adiabatic change or process. So when the change in pressure and volume of a substance, okay, but it takes place when no heat is allowed to enter or leave the system substance, okay, the process is said to be adiabatic. So adiabatic means there will be change in pressure and volume, but the condition is that no heat is allowed to leave or enter the substance. In that case, the process is said to be adiabatic. Okay. So if we see first law of thermodynamics here, dq is equal to du plus dw. In that case, according to adiabatic process, no heat. No, where is it? No heat is allowed to enter or leave the substance. No heat means so dq should be zero because in first law of thermodynamics dq is the amount of heat. Okay, and that results in internal energy du and work done dw. Okay, so since dq is equal to 0, okay, so du plus dw equal to 0, so du will be minus dw. Okay, Therefore, in an adiabatic process, the increase in internal energy is the external work done by the gas. Okay. So why? Because dq is equal to 0, and this is first law of thermodynamics. Dq is equal to 0 means q plus dw. That means the change in internal energy is equal to the work done on the gas or by the gas. Okay. Okay, there is a thing. So when work is done by the gas, that means the volume of the gas increases. Volume of the gas increases means PdV quantity will be positive. Okay. And when work is done on the gas, PdV quantity will be negative. So here you see increase in internal energy. Increase in internal energy will result in work done on the gas. Okay, work done on the gas means it will be a negative quantity PdV. Okay, minus dW. So when internal energy decreases means if there is a negative symbol, negative du, that means it will be positive dW. That means work will be done by the gas. Work will be done by the gas means it will be positive, no, plus PdV. Okay. So these things you should remember. Work done on the gas means uh, the volume of the gas will decrease. Okay, so work done will be negative, and work done by the gas means volume of the gas increases. That means dW will be a positive quantity. Okay, so I hope this is clear. Okay, now adiabatic expansion. So what is an adiabatic expansion? Adiabatic expansion is when the volume of a substance increases or pressure decreases. Okay, volume increase means pressure decrease. In an adiabatic change, the process is known as adiabatic expansion. So expansion means increase. Increase in volume is expansion. Similarly, what is adiabatic compression? When the volume decreases, in that case, it is called adiabatic compression. When pressure increases, the gas compresses, and where the pressure decreases, the gas expands. Or in other words, pressure decrease means volume increase. Volume increase means the gas is expanded, and volume decrease means the gas is compressed. Okay, expansion means increase in volume, compression means decrease in volume. Okay, so is this clear? What is adiabatic expansion or adiabatic compression? Okay.
Yes, sir.
Yeah, okay. Give me a moment. Okay, so what is the like equation of state, ideal gas equation? It is PV equal to constant. Okay, K suppose. This is the equation of an ideal gas. Okay, but in adiabatic process, this equation is modified, somewhat modified. How is it modified? It becomes something like this: PV to the power gamma equal to constant. Okay, this is the, here you see adiabatic equation of state. Okay, adiabatic equation of state means this is the adiabatic equation of state. P to the power gamma is equal to K. Okay, and this is in like no ideal gas equation is PV equal to K. In adiabatic equation, PV to the power gamma is equal to K. Now, what is this quantity gamma? The quantity gamma is nothing but the ratio of the specific heats. Okay, ratio of the specific heats Cp over Cv. So Cp is specific heat at constant pressure, and Cv is specific heat at constant volume. Okay, so that means PV to the power Cp over Cv equal to K. But Cp over Cv is simply given by this quantity gamma, and this is the adiabatic equation of state. Okay, So actually, deriving the adiabatic equation of state is not required for our syllabus, but you have to remember this. Okay, you have to remember the expression for adiabatic equation of state. So in this book, they have no, they have derived the equation. So you can learn the derivation, of course, no problem. But if you have to learn it, it will take some time, and the derivation is not in we don't need it exactly. So here, so after all these derivations, they reach this. Okay, let me stop the annotation. In annotation, this pen size is very thick. Now I have to. How can I reduce the pen size? Okay, anyway, no problem. So you see this expression PB to the power gamma equal to is something e to the power constant. E to the power constant is nothing but it's a quantity called K. Okay. This is the adiabatic equation of state. So the derivation is not required, but you have to remember it. Okay. That means if P1, V1 are the initial states of a gas, that means if initially a gas is having pressure P1 and volume V1, and finally we have the same gas having pressure P2 and volume V2. In that case, the equation of state can be written as P1 V1 to the power gamma equal to P2 V2 to the power gamma. Okay, PV to the power gamma for different states, the multiplication will remain constant. So PV to the power gamma means PV to the power gamma equal to constant means the multiplication of pressure and volume to the power gamma will remain constant. So P1 V1 to the power gamma is equal to P2 V to the power gamma. Okay, so this is a constant quantity. Okay, so this is the equation of state. And now so today we are going to learn about this thing, uh, work done in an adiabatic expansion. Okay, yesterday we learned about work done in isothermal expansion. So today's topic is work done in an adiabatic expansion. And in order to learn about the work done in an adiabatic expansion, this expression is, you should remember this expression, or this expression will come into picture. We will require to learn this expression. Okay, this will be used in picture. This will be used to derive. Okay. Okay. So these things are not that required. So this book, I don't know which book, whether you are following any book or not now. Of course, if library is open, you can use, of course. But uh, this book, this no, what book is it? Refresher course. Here, many numerical problems are given, so you can start solving the numerical problems from here, so that it will be good for you in competitive examinations in future. Okay. So this is, you see this relation gamma is equal to Cp over Cv. Cp over Cv is the ratio of specific heats or the quantity gamma. Okay. Slope of adiabatic and isothermal curves. So okay, this one also I want to show you quickly, because when we learn about Carnot's engine or Carnot cycle, in that case these slopes you have to learn about these slopes. These slopes, no, this is for adiabatic and this is for isothermal. So adiabatic slope is more. No, adiabatic curves have, this is the adiabatic, this is for isothermal. Okay, A means adiabatic and I is isothermal. So derivation etc. These are not required. They are not included in the syllabus. So I am not going to do those things, because we have to learn a lot of things, a lot of numerical derivations. But for now, you understand that the adiabatic curve is more steeper, or it has more slope. No, more, some curve is more steeper means it has greater slope. It has greater slope. Okay, so adiabatic curve has greater slope than uh, isothermal curve. Okay, so here it is written somewhere. Here this line you see. In other words, adiabatic curve is steeper than isothermal curve, okay, because adiabatic curve has more slope. At a point, okay, so at a point where they intersect, no? Or the slope of adiabatic curve is gamma times the slope of isothermal curve, okay. So slope, I'm just writing SLOPE, slope of adiabatic, in subscript I am writing adiabatic, it is gamma times. Gamma means again nothing but the ratio of the specific heat that we have already learned. I, isothermal, okay. The slope of adiabatic curve is gamma multiplied by the slope of isothermal curve, okay. That means adiabatic curve is greater than the, steeper than the isothermal curve. And gamma is having a value greater than 1. Why? Because specific heat at constant pressure is always larger than specific heat at constant volume. And since gamma is nothing but Cp divided by Cv, therefore since Cp is always greater than Cv, therefore gamma is greater than 1. Okay? I hope up to this much it is clear. But anyway, derivation is not required for our course. I am going to the derivation directly. Yeah, this E adiabatic is equal to gamma multiplied by E isothermal, where gamma is nothing but Cp over Cv. Cp specific heat, Cp specific heat at constant pressure, and Cv is the specific heat at constant volume. Okay, let me go to the main topic of today. Work done. Okay, work done during isothermal. This is we have learned already yesterday. So this is what we have to learn today. Work done during an adiabatic expansion. So if the process is adiabatic, that means you have not supplied any heat to the material from outside, but there is a change in volume and pressure. Okay, if volume increases, pressure decreases. So how will you be able to calculate the work done in such a process? Okay. Anyway, so let us, the same note I will give to you, and if you have pen and paper with you, you can also try to note down the important parts, at least the mathematical part I expect you to note down. Okay. Okay, so consider a gram molecule of a perfect gas. Okay, so just like yesterday, gram molecule means 1 mole of a perfect gas contained in a perfectly non-conducting cylinder. Okay, non-conducting cylinder means why we need a non-conducting cylinder? Because the process is adiabatic. Adiabatic means there should not be any heat coming to the system, or there should not be any heat going out of the system. Therefore, the process has to be adiabatic. Okay, non-conducting cylinder fitted with a non-conducting piston. The piston itself should also be not conducting because we don't want any heat to enter the system or heat to leave the system. That's why the conditions are non-conducting cylinder and non-conducting piston. Let capital V be the volume, capital P be the pressure, and capital TK be the temperature of the gas. Okay, so PVT are pressure, volume, and temperature of the gas. Just like yesterday. If now the piston is allowed to move suddenly outward, the gas expands and does some work. Okay. Now you have not applied or supplied any heat, but you slowly move the piston upside, okay, or outward. If you take the piston outward, what will happen? The volume of the gas will increase, okay, and when the volume of the gas increases, that means the gas does some work, okay. or if the just today we have learned, if volume increases, volume of the gas increases, the gas does some work, and if the volume of the gas decreases, that means work is done on the gas. Okay. Since no heat is supplied from outside, the change is adiabatic. Okay, the change is adiabatic because we are not supplying any heat from outside. So yesterday, if you remember a work done in an isothermal expansion, we had a heat source at the bottom of the cylinder, so that when the temperature of the gas decreases because of work done by the gas, so that the temperature can be maintained at a constant temperature T Kelvin. Okay, that's why we fitted a heat source at the bottom of the cylinder. But in this case, we don't have any such heat source because we don't want to supply any heat from outside. Why? Because we want to calculate, or we want to find the expression for work done during this adiabatic expansion. Adiabatic means no heat is allowed to pass from outside, or no heat is allowed to leave the system to outside. Okay. And since the process is adiabatic and the energy is drawn from the gas, due to which the temperature of the gas falls. So you are taking the gas is doing some work because its volume has increased, and because of the work done by the gas will expand and its temperature will fall, because when a gas is expanded, gas increases its volume, its temperature decreases. Okay. And when a gas is compressed, its temperature increases. So here in our case, the gas is expanding, that means its temperature is falling. And also we don't have any heat source which can supply heat from outside, therefore the gas temperature will fall in this case. Okay, I hope this is clear up to here, the introduction part. Okay, so now if capital A, just give me a minute. Okay, if capital A is the area of cross section of the piston, okay, just like yesterday, and the piston moves through a distance of dx, okay, just like yesterday we discussed, so that the change in volume is dv. Okay, so dv is nothing but adx. Okay, a is the area of cross section of the piston and dx is the displacement. So dv, or the change in volume, is nothing but area of cross section of the area of cross section of the piston and the displacement of the piston due to the expansion of the gas. Okay, so dv is equal to adx. Therefore the work done is equal to force pa equal to force. Okay, force force is equal to pressure multiplied by area. Therefore, what is the work done? Work done will be pressure multiplied by area multiplied by, therefore work done dW will be pressure multiplied by area multiplied by displacement. Displacement is that of the piston. Okay. But just now we found that ADX equal to dV. Okay, ADX equal to dV. Therefore, dW is equal to PdV. PdV means dW is equal to the multiplication of pressure and the change in volume. Okay, I hope this is clear. So also yesterday we learned this. So dW is equal to PdV. How PdV, it is like this. Okay. Okay, the relation between pressure and volume under adiabatic condition can be graphically shown by the adiabatic AB. AB is the adiabatic as shown in the figure. Then the work done for a small change in volume, dV, small change in volume is dV. You can see in the figure. Okay, dV is the small change in volume, corresponds to pressure P, capital P, and it is given by the area AB. ABDC. It is written ABCD, but it should be actually ABDC. So ABDC, you can see small a, small b, small d, small c. This is the area of this particular region. No? This type of lines, you can see, okay, which is equal to PdV. Okay. Now, yeah. So yesterday also, if you learned that we had a curve, isothermal curve like this. Okay. But here the difference is just now we have learned that adiabatic curve is more steeper than isothermal curve. That's why I discussed that before coming to this concept. This is the adiabatic curve and this is the isothermal curve. So adiabatic curve is more steeper. This is the adiabatic curve and this is the isothermal curve. Isothermal curve is not as steep as an adiabatic curve. Okay. That's why this AB, this is steeper. Okay. Same as yesterday in this figure, but here this curve has to be steeper. Okay. Okay, now we need to calculate the work done. Okay, so in order to calculate the work done, our pressure is constant. Okay, at a constant pressure, if we have to find the work done for this volume dV, okay, pressure is not constant; it is actually decreasing. But for a very small portion dV, we may consider that the pressure is maybe maybe constant. How we can do, yesterday we showed that PV equal to RT. Now PV equal to RT is the equation of state for an ideal gas. But here our gas is ideal, but it is the process is adiabatic. Therefore, this is the equation of state that we discussed at the beginning of today's lecture. Okay, PV to the power gamma equal to K, where gamma is again the ratio of the specific heats. Gamma is Cp over Cv, which we already discussed. Cp divided by Cp, specific heat at constant pressure and specific heat at constant volume. Therefore, what is pressure quantity? Pressure is K divided by V to the power lambda. K is a constant. Okay, K is nothing but a constant. So don't worry about that, capital K. So P, capital P is equal to K divided by V to the power lambda. Okay, is it clear up to this? Now work done is again, the gas is expanded, so work done is again P d V. Okay, now what is P? P is this one, P V to the power gamma is equal to K, therefore P is equal to K divided by V to the power gamma. So in place of P here, if we just come here, come down, so here I will write, so work done, what is the, okay, sorry, this is dw, this is not w, but this is actually dw. So what is dw? Dw will be P value is K divided by, so here P is what? K divided by V to the power gamma, K divided by V to the power gamma, then dv is already there, this dv, this is the dv, d, okay, yeah. So dw, the work done is nothing but K multiplied by dV divided by V to the power gamma. So I hope you have understood up to this. This is not that difficult to understand. Okay. Only thing you have to recall is that, remember, is that this is the equation of state. This one is equation of state for an adiabatic process. Okay. Okay. If we have learned up to this, then we can technically find the work done. Okay, let me remove these annotations so that I can go below. Yeah. Okay. Hence, the total work done for the gas, when the gas expands adiabatically from volume V1 to volume V2 is given by. So when the volume increases from V1, this V1 to V2, therefore the total work done in this case is given by capital A, capital B, capital D, capital C. So it is written here A, B, C, D, but it should have been actually A, B, D, C. Okay, capital A, D, B, C. Okay. So have you understood? So for this small, for a small change in volume dV, the work done is small a, small b, small d, small c. for this large change in volume of the gas from V1, capital V1 to capital V2, it is given by this area, capital A, capital B, capital B, capital C, just like yesterday. Okay, so same thing, but here the equation of state is this one slightly changed. Okay, okay, given by A, B, C, A, B, D, C actually included between the adiabatic. Okay, A, B is called the adiabatic curve now. Included between the adiabatic AB and the ordinates AC and BD. AC and BD. Ordinates, no? Ordinates means the value along y-axis. So adiabatic AB and between AC and BD. AC and BD are the ordinates, okay, which corresponds to volume V1 to V2. Okay, I hope you have understood this particular figure completely. It should not be a problem. Okay. Okay, so total work done, that we have to calculate. So how we can calculate? We can calculate the total work done from this expression. No? If you can just integrate this expression dW is equal to K multiplied by this, then total work done integration of dW is equal to integration of K dV to the power V to the power K divided by V to the power gamma. Okay. Now gamma minus 1 minus gamma 1 minus gamma. So here I don't know why they have written V2 to V1. It should have been actually V1 to V2. Okay. So total work done, it should be K multiplied by K multiplied by integration of V1 to the power V2. In this book it is written V2 to the V2 to V1, so it should be actually V1 to V2. The rest of the things remains same, dV over sorry, let me remove this. dV over V to the power gamma. Okay, so now if you integrate, what is the integration? So should I show this integration or you understand this? So okay, so let me just integrate dV over V to the power gamma. Okay, dV over V to the power gamma. So you can write this as integration of V to the power minus gamma dV. Okay, so if you integrate this, it will be what? It will be V to the power minus gamma plus 1 divided by minus gamma plus 1. Okay, or simply writing V to the power 1 minus gamma divided by 1 minus gamma. So that is what, no? V to the power, this is 1. Okay, the 1 is separate. Yeah, V to the power 1 minus gamma divided by 1 minus gamma. So that is the thing, V to the power 1 minus gamma divided by 1 minus gamma. Of course, K is a constant, so K is not included in integration. And 1 minus gamma is also constant. Gamma is a constant value. Okay, so constant means for a given gas, be it monoatomic, diatomic, or triatomic, gamma is a constant quantity. Okay, therefore, so more about the ratios we'll learn later in one of the topics. So, but for now, you should learn that gamma is a constant quantity. So K divided by 1 by gamma is outside, but now volume is changing, so V1 to V2. Okay, since the volume is changing, therefore we have to integrate this quantity, specifically the volume quantity V to the power 1 minus gamma, and the change is from V1 to V2. Okay, so again K divided by 1 minus gamma, it is there. Now you just integrate this, it will be 1 divided by, again they are taking like now v to the power gamma minus 1. So this is what we get. I hope this is just simplification of from here. Okay, so I think you know, all of you, I assume all of you know this integral calculus. So this is just the integration from here to here. Okay. Now one thing is that this quantity gamma is actually greater than 1. Okay, because we have already know why, because Cp is greater than Cv. Specific heat at constant pressure is greater than specific heat at constant volume, and therefore the quantity gamma is greater than 1. So what they have done is that they have made 1 minus gamma equal as gamma minus 1. Why gamma minus 1? Because actually gamma is greater than 1. Okay, so k divided by gamma minus 1, and when you are doing gamma minus 1, then what will happen? So here you see v1 quantity was negative, so 1 divided by v2 to the power gamma minus 1, and minus 1 divided by v1 to the power gamma minus 1. So they are making a gamma, they are making this a negative quantity, so they are also making this negative quantity. So k divided by gamma minus 1 is equal to 1 divided by v1 to the power gamma minus 1 minus 1 divided by v to the power gamma minus 1. Okay, so have you understood this expression? Now tell me, who understood this, who has not understood this derivation? It's just integral calculus. It is nothing that difficult. Integration. And here just gamma is written first, then gamma minus 1 is written because of this reason. The reason is gamma is actually greater than 1. Okay, because specific heat at constant pressure is greater than specific heat at constant volume. Okay, so I hope this is clear, since nobody is speaking anything. Okay, so we can further simplify this expression. Okay, this expression can be further simplified. How? Okay, I'm removing the annotation. So we have already learned
This will
this.
be
Yeah,
Google
so,
Classroom.
huh?
This will be uploaded in Google Classroom.
Yeah, the video will be there. Video, the note, not, because I have not yet made the note, but this is the same note I will make. Okay,
Yes.
but the video I will upload in class. So by today itself, I will upload the video. Anyway, so I hope up to this much it is clear here, up to here clear. But again, we have learned about this. Okay, P1. Why somebody written something in chat? Okay. Where is the annotation? Okay. So we have already learned about this. So PV to the power gamma is a constant, right? This one we have learned. Or when the gas is changing its pressure from P1 V1 to P2 V2, then we can also write like this: P2 V2 to the power gamma equal to K. Okay, we can also write like this. So this so W from here, if we're coming here, so W work done is equal to 1 divided by gamma minus 1. Okay, and K quantity has been taken inside. That means K divided by V1 to the power gamma minus 1. Okay, so here it is directly written that P1 V1 to the power gamma and P2 V to the power gamma. Why? Because of this particular relation. Also given here same relation as this one. Okay, and K is taken inside for simplicity of calculation. Okay, so here we have only 1 divided by gamma minus 1, and K is here. So K is P1 V1 to the power gamma, P2 V to the power gamma. Then again, if you simplify, 1 divided by gamma minus 1. Okay, and so P1 is there, so V1 to the power gamma divided by V1 to the power gamma minus 1. So if you just divide V1 gamma divided by V1 to the power gamma minus 1, we will be left with only V1, P1, V1. Okay, P1 is there already, we have P1. Similarly, this second quantity will be P2 and V2 to the power gamma, V2 to the power gamma divided by V2 to the power gamma minus 1. So we will be left with only V2 and P2 is already there. So the work done is nothing but 1 divided by gamma minus 1 equal to P1 V1 minus P2 V2. Okay. So have you understood the derivation up to this? So this is the work done, nothing else. Okay. So I think this should not be that difficult because it is just you have to start with this equation of state for adiabatic gas, and of course the work done. What is the work done? PdV. So P is replaced by, look, pressure was replaced by K divided by V to the power gamma, but ultimately what we are doing, we are having the K quantity and we are getting back our pressure terms. So this way you can actually simplify the expression for work done during an adiabatic process. Okay. So anyway, you can further simplify this equation because you see you have P1 V1 equal to P2 V2. Then for ideal gas, so P1 V1 equal to RT1, you know this, and P2 V2 is equal to RT2. Okay. So P1 V1 RT1, if you write here RT1 minus P2 V2 is RT2. So R can be taken common. This R is universal gas constant. So it will be work done is equal to R divided by gamma minus 1 and to RT1 minus RT2. So T1 minus T2 will be common. So this is one expression, this is one expression for what? This one. And this is another expression for what? Okay. So if you are like given this, so it may be asked in numerical, no? You may be either given like gamma is given and P1, V1, P2, V2 are given, you can calculate W. And also if you are given the changes in temperature T1 and T2, then you can also calculate W. So gamma will not be directly given, gamma will be given as like monoatomic, diatomic or triatomic like that. So monoatomic gamma is some different value, then diatomic gamma has a different value and triatomic gamma has a different value. So gamma will be given like that. It will not be, you will not be given the exact value, but you will be given that the gas which you are dealing with is either monoatomic, diatomic or triatomic. Okay. So this way you can derive. Okay. So R divided by gamma minus 1 multiplied by okay. So let me just focus on this last expression. W is equal to R divided by gamma minus 1 multiplied by T1 minus T2. So in adiabatic expansion, what we learned at the beginning, you have not supplied any heat, but the gas doesn't work because the volume is expanded. Okay, when the volume is expanded, the temperature falls. Okay, that we discussed. Temperature falls means actually T1 temperature, the initial temperature of the gas is greater than the final temperature. Okay, this is the temperature of the gas after expansion. This is the temperature of the gas before expansion. So T1 is greater than T2. Therefore, in this expression of work done, actually T1 is greater than T2 and gamma is greater than 1. We have learned T1 is greater than T2. Therefore, this work done is a positive quantity for expansion of the gas. Okay, let us see what is written here. This shows that the work done during an adiabatic expansion is proportional to fall in temperature. This quantity is the fall in temperature T1 minus T2. On the other hand, there is an adiabatic compression if the temperature of the gas will increase, which is proportional to work done. So when the expansion is there, T1 greater than T2. When the compression is there, the gas temperature will rise. That means T2 will be greater than T1. But for now, if I ask you to, in examination, calculate the work done in an adiabatic expansion, This is the one you have to do. Okay. Adiabatic expansion, the final temperature is greater than the initial temperature. Why? Because when the gas does a work, the gas volume expands, and with the expansion of the volume of the gas, its temperature falls. Okay. I hope this is clear. So I am cancelling the share. I think of course we are almost done with today's session. Also, in 1 or 2 minutes it will end. Okay.